So much again, Remy, for sharing. Thank you, Martin, for agreeing to speak. And I just hand over to you, Remy, now.
Okay, well, thank you. So I wish I was here in person to share and exchange with everybody before and after the meeting. But I'm glad to have the opportunity to share this presentation that will be given by Martin. Martin Berger is head of the chair of applied math at the University of Erlangen. His group focuses on universe problem, mathematical imaging and PDEs. And today we'll talk about the Bregman framework for sparse neural networks. So, well, without further ado, Martin.
So thanks a lot for the opportunity to present some recent work here. Something we did with Leon, who is very recently moved to Bonn, and Tim Reut and Daniel Tembrick, who are still in my group. So what we are interested in is a framework for training sparse neural networks efficiently and ideally with similar effort than standard training and with similar methods. Well, I mean, the motivation, I think, is quite clear. Everybody wants to have, for complexity reasons and other issues, as small or as compact networks as possible. So this is why, we want to go for sparse neural network. And of course, another issue in the end, which is a bit tricky, is the energy consumption. Of course, if you have in the end a compact network, it's efficient to evaluate these sparse networks, but the tricky thing is, of course, the training. So this is something we can still discuss, whether our training is so much more efficient than other training methods. And I will particularly come to that in the end. And of course, there are theoretical issues which are also not clear. This is more a conjecture that sparse neural networks, of course, well, I mean, they're less likely to overfit the training data. That's probably clear. It's not clear how much better generalization properties or things like this you will get. There are also some results which tell you that overparameterization can be beneficial, but we want to follow that route. And we followed what is called this lottery ticket hypothesis, that each dense neural network contains an equally performing sparse subnetwork kind of. So of course, if you think about simple feed-forward architectures, then instead of fully connected, we want to be as sparse as possible. Okay, we are of course not the first to try this, and there are kind of different paradigms. We would call this dense to sparse, sparse to sparse, or some other methods. So if you do dense to sparse, you basically try to train a dense networks, and then by pruning or some other kind of approaches, you throw away connections that you think are not important. Okay, there are two examples of papers. There is some recent approaches to directly get sparse networks by, for example, evolutionary training, and there is something which is a bit in between, I would say, and this is what we follow. Is we do some kind of inverse scale space law or Bregman iterations for L1 type penalties in order to train sparse networks. So the catch is, as you will see, is basically we could say it's sparse to sparse. We will start with a network that is extremely sparse and make it a bit more denser until kind of it satisfies some theoretical bounds. The catch is at some points we also have to, we have some kind of virtual nodes in the network, so virtual connections. So, or could say some weights which are basically zero. And at some points during the computation, we have to do something about these zero weights. So we have to do some computations sometimes there. So this is why it's not completely sparse to sparse. So as you would put it, and you will see this when I explain the methods, it's either very sparse to sparse, or it's in another sense also dense to sparse in terms of some computations. Okay, yeah. So what we do is, of course, I mean, ideally in inverse scale space flow, you would start with everything zero, which of course does not work for a network. If you train weights, all weights being zero, then the initial networks will be quite useless. And there are, then we add, of course, some necessary parameters or weights to reduce the energy until we get to some recently converged state. And as usual in all these kinds of implicit regularization approaches, we are not iterating until full convergence, but we use an appropriate early stopping. Yeah, and a similar approach based on Bregman iterations, but far not with that level of training methods that we developed now, was first proposed by Huang et al. In 2016. And then there is a paper on, actually by Martin also, I think, with Carola. And wisely, the camera is zooming most of the time to Martin, banning for the audience now. So this is something that is also related to our work. But just to illustrate the standard idea of Bregman iterations, not for neural networks, but as we did it many years ago for image restoration. So you start with basically nothing, a zero or constant gray value. And here, yeah, if you train, for example, with total variation, then you gradually build up finer and finer scales. Here we stopped quite early, and you see, yeah, you get the main features after some point, depending also on what kind of regularization you use. So here we are in a setting of sparse edges. Okay, so how does it look like if you have a general penalty J or regularization functional? And we do this for denoising with an L2 penalty. You would start basically with, yeah, initial value 0, and in particular corresponding subgradient, which is 0, P0. So in the first step, this is not there. So you solve a standard denoising problem with some parameter. And then the important point is you update the residual. So in this L2 setting is actually the same as an augmented Lagrangian method. So you have a simple update of the residual, and then you could, yeah, either see it like this here, you add back the residual to get a new kind of data that you then denoise again, or you equivalently rewrite the whole thing by expanding the square here as what's called the Bregman iteration. So you would say in each step, instead of penalizing with the original functional J, I penalize with the Bregman distance to the last iterate. Okay, so this is the Bregman interpretation of this method. Okay, and just to remind you of the Bregman distance, or Bregman divergence, as it's called in statistics, corresponding to a convex functional, is, yeah, kind of the first order Taylor expansion around point V. So it's a non-symmetric, or in general non-symmetric, in some cases it is, but typically it's a non-symmetric distance, and it's also not necessarily a strict distance if J is not strictly convex. Okay, so here roughly this is what it looks like. If you have a point here and another point here, and this is the functional J, then do the first order Taylor, or compute the tangent, and then you measure this distance between J and the tangent to the other point, and this gives you the Bregman distance. And of course, if you would do it, see also the non-symmetry here, if you would do it in the other way between this point and this point, you would put this tangent and take the distance here, which could be a different value. Okay, so we can, of course, in the Bregman version, it's very easy to generalize this to arbitrary loss functionals. So we can replace this quadratic fitting term by any loss functional. And what we have to do here is, of course, minimize the corresponding problem with the Bregman distance and do the update based on the gradient of the loss function. Okay, we will also assume here we have a differentiable loss function. In the end, we will also mainly deal with differentiable J, or no, not really, but important. So this is a very simple thing to compute, and here you have to do an appropriate minimization, which is as difficult as solving the original penalized problem. Okay, and of course, doing this, as I said, each step in the iteration is like solving one regularized problem. So computationally, this is not really what you would like to do. Though you get better results than with the standard methods, you would like to have some cheaper versions. And one idea is, again, to cheat here a bit and to linearize this term. And this is what is then called the linearized Bregman method. The only issue you have to take here is this does not work if J is not strictly convex. Okay, when you linearize here and you have something that is not strictly convex here, like for example L1 or total variation, then you basically have two linear or more or less linear functionals, and it could be that this becomes unbounded from below, so that you don't even have a minimizer, and also that even if you have a minimizer, the steps can be far too large that you take here by minimizing this. So what you would like to do instead, or what you would like to make sure, if J is not strictly convex like L1, you would like to add something, for example, like some parameter times the L2 norm squared or some Hilbert space norm squared in more general settings. Okay, and then once you have achieved a suitably convex or strictly convex functional here, you can do these linearized Bregman iterations. And if you somehow compare the optimality condition with the original one, in the original setting, the optimality condition would be to have here UK plus 1 instead UK. So if you rewrite this here, we have some kind of a first half step, which is just the gradient method. Okay, this is just one step of gradient descent. And then the second half step would be to evaluate the proximal operator for this smoothed for convexified functional delta times J. Okay. And just for completeness and also for some analysis, some nice analysis things, there is a continuous time limit that you can think of. So like you go from gradient descent to gradient flows, you can go here with tau, the step size to 0, and then you arrive to what is called the inverse scale space method. So it's a doubly non-linear differential equation actually. So you have here an ODE for the subgradient, which is driven by the gradient of the loss. And you get a very similar form here in the linearized Bregman iterations, but of course the linearized Bregman iteration rather corresponds to an explicit time discretization, whereas the original Bregman iteration is an implicit time discretization. Okay, so now how will this work for training neural networks. And of course, so far I had a generic unknown U. If you talk about neural networks, we call the parameters theta, and sometimes we'll call them weights, so they will be called W, but now in the theoretical part, we just rewrite everything, just calling you theta now. Okay, so this is again the linearized Bregman method we just wrote down, and we have here some auxiliary variable for the gradient descent step, and then we have the proximal step to get the new parameters. Okay, what we want to do is we want to train sparse networks. So clearly we want to choose something like the L1 norm, or later, more importantly, we will have some kind of group sparsity, group 1 norms to train suitable sparsity, as I will explain later. Okay, and of course, the functional L, the loss, will be the empirical risk that we have on which we train. Okay, the difficulty now is the usual one that you always have in training networks. The loss typically is non-convex, and computing the full gradient is quite tedious. So we will try to get the usual kind of ideas of stochastic gradient descent and things like this into this Bregman framework. And the other problem is what I told you before, is when we do this on images, we start with 0 or some trivial image. And of course, starting with all parameters equal to 0 in a neural network will not work. So then you will start with typically some stationary point of the loss and not move anywhere. So we have to come up with some other initializations. Okay. So what we do in order to overcome this, okay, just look at one unit, typical unit in a deep network, sigma being the activation, and W the weights, be the bias. So we follow some approach that people have done before. We do some masking with Bernoulli random variables to get something that is initially sparse or reasonable. And for these random initial weights, we also try to keep the variance reasonably small. So with some choice depending on the number of nodes in these two consecutive layers. Okay, so this is something that some sort of people have done before, so that's not the really new stuff. Just to tell you, we have to be careful a bit with the initialization. Okay, now what we want to do, of course, is we want to choose some kind of stochastic or batch gradient descent method. So instead of having the full empirical risk on the whole set of training data, we want to minimize in sub-steps only the risk on some batches. So what we do is the same as before. We compute like a stochastic gradient descent step on this batch that we choose randomly. So up to here, and then we choose a proximal step again, as we would do in the linearized Bregman. So in this way, okay, you can say the first two lines are exactly what you do in stochastic gradient descent, and then you just add this proximal step. So in comparing to standard training, this is basically the same effort. Computational effort goes into the backpropagation, and if you do a proximal step for L1 or group L1 norms, this is basically for free compared to the gradient computations. Okay, and we could generalize further as we do in stochastic gradient descent. We could also, before we do the proximal step, we could add the usual momentum-based variables. So kind of add another variable m, which is the momentum, and update also based on this variable. Okay, so, and if you employ the Adam update rules, we get what we call the AdaBreg algorithm, or Adam Bregman, whatever you want to call it. Okay, so basically you can generalize these things, and it turns out computationally looks reasonable, but the question is, does it make sense if we join that with these proximal operators and this whole Bregman iteration framework? Is that still a reasonable and a convergent method? Okay, so what we can analyze is this kind of stochastic Bregman iteration. So we draw some kind of random variable that describes the batch randomly, and then do some random gradient descent step, and then do the proximal step with the functional J. Okay, and just keep in mind, J is still assumed to be convex, otherwise the proximal does not make so much sense. Whereas the loss in general can now be non-convex. And we have some estimator of the gradient of the loss. So you could think of a batch, if you randomly choose a batch and make this, it's an unbiased estimator of the gradient. Okay, and this is also what we need as standard assumptions, again, very similar to stochastic gradient descent. The first assumption we always need is, of course, this unbiasedness. So the expected value of this gradient estimator is really the loss gradient. And not surprisingly, we also assume a bound on the variance for this estimator, which we call sigma squared. Okay, and yeah, as probably you all know, this batch estimator is of course a standard example satisfying these properties. Okay, then we further assume that there is some kind of smoothness of L. So basically what we assume is that the gradient of L is Lipschitz continuous with some constant, yeah, again L. So the notation maybe is not perfectly optimal. And for some results, if you want to get strong convergence rate results or things like this, we will need to assume convexity of the loss and some kind of strong convexity here with some distance. And don't worry that there is no distance squared here, as you would expect, because the way we write the distance is, we would say, okay, the distance squared is our d. In the Euclidean case or in the Bregman case, the d is just a Bregman distance. So if you want to get some strong, for example, some convergence rates of Bregman distances, we will need to assume some kind of convexity like this, with d being the Bregman distance. Okay. Yeah, and by the way, usually it's very hard to have these assumptions in the Bregman distance. It's not so hard in our case because there is the quadratic term here. So the fact that J delta consists of like an L1 term plus an L2 norm squared or something like this yields that this convexity condition in the Bregman distance is not so far from the convexity condition in the Euclidean case, actually. Okay. And then what can we prove? So if we do a standard estimate combining the main ideas of stochastic gradient descent and of the analysis of Bregman iterations, we can show that basically the loss up to the usual variance term multiplied with step size is decaying, and that happens even without any convexity assumption. So that's not too surprising result. And well, if you ever looked into convergence analysis of proximal or Bregman method, you will not be surprised that here, instead of the usual squared norm between two consecutive iterates, you find here the Bregman distance, and in this case it's the symmetric Bregman distance, so the sum of the two non-symmetric ones. And on expectation, you will see that this is then decreasing, or what you also see immediately, if the step sizes are summable, then the sum, this sum will be finite. So you expect that the difference between consecutive parameters at least goes to 0, and essentially up to the variance, the loss is decreasing. Okay, and this is a stochastic kind of generalization of the results that Martin and others derived in this paper, 2018. Okay, if you want to have some kind of stronger convergence of the iterates, we need to assume a bit more. So basically, we need also to add a convexity assumption, and we need to have some properties which are not so, well, basically the same as in stochastic gradient descent, some properties of the step sizes. So they should be square summable but not summable, and non-increasing. So the standard example that you might think of, 1 over k, works, and then you can prove with this additional convexity assumption that the so the mean squared distance between at least a subsequence of iterates and a minimizer of the loss converges to 0. Okay, I don't go too much into the detail. Just show you that actually, again, in the Bregman distance, or in the expected Bregman distance, the convergence is a bit nicer than in the L2 formulation. So with a weaker condition on tau k, we get convergence of the whole sequence in the expected Bregman distance. And if we choose tau like 1 over k, we even can prove a convergence rate of 1 over k in the Bregman distance, of course, only under the additional convexity assumption. Okay, so far the analysis. Now let's go to some results and what does it really help to train neural networks. So we start with something very simple. We just train a standard deep multi-layer network, and we just put now the sparsity on all the weights. Okay, so and you see what happens if we train this. So compared to standard stochastic gradient descent, we are in the same level of accuracy with this kind of linearized Bregman's methods, but of course we are at a much lower L1 norm and a much lower number of non-zero entries. Okay. The question is, at this point, does it really help to get sparsity in this way? If you penalize the L1 norm, you enforce many of the weights to be 0. So this is like in my first picture that I had. So you kill some of the links in the networks, but you still do not eliminate nodes in the network. So for this, you might have to use other regularizers like group sparsity that I will come to in a minute. So for example, in a standard convolutional network architecture on several layers, we can put a group sparsity on the convolutional kernels, and then we end up with a network where most of the convolutional layers really are 0. So here we have a little visualization of the first convolutional layer, And you see, we start with something where most of the convolutions are 0. And then with the Bregman iterations, we gradually add and slightly modify some of them. And you see, if you compare iteration 20 to 100, you see already that this is already gone to a steady state. Actually, after very few iterations, you add the convolutions that you need, and you keep the others 0. Okay. Another example would be then to have a residual network. So this is an example on the CIFAR-10 data set, and you see here a comparison in the training accuracy to standard methods, which is of course in the same range also with the test accuracy, but we actually arrive at training much sparser networks, of course, in the end. The maybe more interesting point, that you can do is really to try to compute full neural architectures with our approach, and then the group sparsity becomes even more important. So one thing that you could try is to kind of see, can you automatically get certain architectures, like for example for denoising some autoencoder or residual autoencoder networks. That here's just some results on denoising standard MNIST characters. And now we can think of what would be the possible sparsity goals, or the groups for sparsity that we could penalize. So one thing that is quite attractive is kind of to have as few neurons as possible. So we could say, okay, we take a group sparsity and take one group just as all weights in the network that are connected to one neuron. We do this for each neuron. And if we get this kind of group sparsity, we have as few neurons as possible in the network. So we start with some, maybe simple architecture or fully connected network. And then we try to train it such that most of the neurons never really appear because of this group sparsity. Okay, and if you have residual networks or more skip connections, what you could also do is try to get some sparsity on skip connections. So we call these skip weights in the skip parameters tau. And something that you could also do, for example, in residual networks, is try to train a network that has as few layers as possible. Okay, if you train a residual layer and all weights in this residual layer are 0, then it's just the identity. So that is just like if this layer was never there. And keep it in the end. So we can just put all weights corresponding to one layer and put a group sparsity there. Okay, for the last one, I still don't have very good results, but for the other, I will show you some. So what we will study here is two kinds of regularizers. One is a group sparsity on the rows. So this is corresponding to the first one. So here we have as few neurons as possible with that prior. And then we studied two options on the skip parameter. One is some of the indicator function at 0. So this is just a complicated way to write that we train a neural network that has no skip connections. And in the second, we want to have sparsity or as few neurons as possible, but then also as few skip connections as possible. Okay. And you will see automatically, I mean, that's something you can find easily if you have a neuron that is not there. So if all these weights corresponding to this neuron are 0, then you will also find automatically with this sparsity prior that all skip connections to this neuron are 0. Because if you won't do a skip connection there, then you cannot propagate further. So it will not change the energy, but the L1 term will decrease the energy if you remove the skip connection. Okay, so these two are written here independently, but they also, of course, in the end, concerning the results, it's a bit connected. Okay, so how could we do this? So we start here with a simple architecture with 7 layers. We allow in each layer up to, I think it's the same number of 800 something that we had in the first layer, but we start initially with something very sparse. So this is what is, yeah, here visualized as the white part, the number of layers in the initial value. And then you see the method automatically learns an autoencoder structure. So you very rapidly, already in the first iterations, you get to the number of output neurons that you need to perform this denoising task. Whereas slightly slower, you increase the number of neurons in the middle layer. Okay, and this is what we get in this case without any skip connections. Okay, it's also interesting to look how these things look like when we do it for different tasks. So the first, basically repeated again, this is a denoising task, and the second one is a deblurring task with the same data sets, and overall this kind of data here is the distribution of these autoencoders. And I forgot basically what I wanted to point you to. So basically you see surprise. It's, well, maybe not too surprising that the number of output neurons is basically the same. And there is not much variance in these cases, whereas there is quite some change here. And in general, if you do this more ill-posed deblurring task, there is more variance if you do this on different runs, on different data sets in the number of neurons when you do deblurring than when you do denoising. Okay, and then we can do the same, which is maybe also interesting to compare with here. So here again, this case was just to train without any skip connections, and here now the same if we allow for skip connections but want to have some sparsity in those. And then you see when you allow for skip connections, you decrease a lot in the first layers because you don't need so many neurons there, because you can do a lot with skip connections directly to the other layers. And here you see now, if you compare also the deblurring and the denoising architectures, you see a big difference now, whereas in the denoising, okay, there was a bit more variance, but basically the optimal architecture was more or less, or at least in terms of number of neurons, I'm not showing you the full architecture, obviously. At least in number of neurons, this was very simple for denoising and deblurring. When you start doing skip connections, there is really a big change between these two tasks. And if we visualize the typical skip connections between different layers, you see also that in the deblurring task, you mainly do skip connections to the output layers or to the last two layers, whereas in the denoising, it's far more evenly distributed where you perform skip connections. So this is something I find quite interesting, and it's still a challenging question really to interpret further these kinds of results that you get here. Okay, so what have we seen so far? Well, we've seen that Bregman iterations can be applied favorably for training sparse neural networks. We can add, and they can be done basically with the same kind of methods and effort as stochastic gradient descent, so you don't have to restart everything from scratch. We can provide some analysis to make it plausible that they do a good job. We have seen some applications. I personally always find this neural architecture search more interesting than the other training results. And yeah, to give you an outlook, there are basically two questions that one needs to elaborate further, I would say. One is the convergence in a non-convex setting to get better results as we currently have there. From the practical point of view, the more relevant is maybe to get really a sparse training. So what I didn't tell you so much in detail, but if you ever did this method, you know what you have to do. When you perform the algorithm so far, we do an update of every parameter. So we would start actually with a high number of parameters. So if you think about the architecture search, we would have a high number of neurons and weights between them. Most of them would be 0 all the time, but we still have to compute the gradient step and the proximal step. Just the proximal step will give you again 0 most of the time. So there is a lot of computational effort if you do it that way that is really not necessary. So you spend a lot of computing things about neurons that will never appear in the network. So what we would like to do instead is something that we call adaptive Bregman or adaptive inverse scale space. And just to give you an idea, it's nicer, and this is why we want to go to this continuous time version of the inverse scale space. So we have this gradient descent, this generalized gradient descent where P is a subgradient here instead of U. And so let's check what would happen if we do this for L1. If J is the L1 function, then the subgradient or each component of the subgradient is the multivalued sign of the entry here. And in particular, you know, the sign is only relevant really if it's plus or minus 1. If the absolute value of P is less than 1, then you always have U equals 0. Okay. So if you have at some time, okay, you have a P that is say 0.2. Then you know this flow will take a certain time until you can reach plus or minus 1 the next time. And you know in this time, basically you don't have to do anything because the subgradient is less than 1. Okay, and we did this for standard reconstruction setting with an squared non-penalty in this paper many years ago in this case in compressed sensing applications. But we could at least take a similar idea for sparse training. So when you do this for a quadratic problem, you can even exactly solve it and give an exact time discretization and have this adaptive method that minimize the number of computations that you do. What we do here in the non-convex setting with a arbitrarily convex loss is at least an approximate approach. So if you think, what we learn here is basically that for L1, the flow stays piecewise, and I have to be careful, is in terms of the variable U, it's piecewise constant. So the parameters would not change for a while, whereas then you have here the derivative is constant, so the subgradients would be piecewise linear, and this is why how you extrapolate, and that you can also do. So you keep u fixed for a while and extrapolate the subgradient. Okay, then it's a very simple task to do this. And then you can check what is the critical time. Well, the critical time will be the minimum of some of these two numbers here for +1 or -1. So the next times you could reach +1 or -1. Okay, so you could say roughly this is not exact anymore, but this gives you an estimate when is the next time to update the ice component of your parameter. Okay, and so what would be the possible strategies for doing this? Well, one would be somehow a deterministic update. So if you're now at time t in your pseudo time t for the computation, you compute this estimate ti star, and then you say, okay, I keep ui 0 for some time, for example, to be safe, not until ti star, but only for the half of this time interval. Or you could say, if you anyway do kind of randomized method, you also do a random batch in the parameters, and you would say, okay, I select at each iteration step, I select the update of a parameter with some probability that depends on the critical time compared to the current time. So if you are very close to the critical time, we select it with higher probability than if we are very, very far from it still. Okay. And if you want to do this for neural architecture design, we have to generalize this to group sparsity. That's not so difficult actually. So you replace the sign by the value divided by the norm, and still check when the norm gets 1. And we also need to generalize, of course, to this setting of the linearized Bregman.
What are you doing in the?
Excuse me? Was there a question or?
I think, Martin, you can continue. I think there was just someone joined and didn't mute.
Okay. Okay. And yeah. Yeah, and the other thing is we have this delta parameter, but still the proximal has the right property that it stays 0 if the norm is 1, and so you can also change this. The only change with this proximal when we add this delta times the L2 norm is that it's not piecewise linear, but you have to solve a very simple ODE and it gets piecewise exponential, but you can actually compute also that and compute the critical times. Okay, so anyway, this is enough for today, or all the results we have so far. And yeah, as usual, I can thank the collaborators and the funders, and there are these 2 papers that my talk was based on, and if you want to try out some code, also team has assembled all that on GitHub. Yeah, thanks for the attention.
Thank you very much, Martin, for this very nice and inspiring talk. So I think we have time for questions. I may need some help from the local organizers to see if there are questions locally or remotely. And maybe I'll start with a simple question. It's the framework that you designed was to seek sparse or structured sparse networks in a learning context using penalties that such as the L1 penalty or group sparsity penalties that have a long history in inverse problems. Mm-hmm. You have both an analysis of the convergence into some assumptions and convincing numerical evidence of the sparsifying effect of these penalties. But do you also have some hints, mathematical hints, as why what we know in the context on inverse problems regarding the sparsity-inducing properties of these penalties can be ported in the framework of networks? Are these penalties truly sparsity-inducing, and why?
Yes. So for the inverse scale space and the Bregman, it's basically, again, these kind of properties here. In this case, it's more a matter of the prior, really, and you can understand it from the subgradient. So I would say there is a large region where the subgradient, or where it is. So if you see it, for example, for one, basically, if you pick randomly a subgradient, then with probability 1, this will lead to a 0 entry. So only at plus minus 1, this will give you a non-zero entry of the coefficient or of the parameter that it corresponds to. So if we start here with subgradients that are with absolute value less than 1, then we can directly see that for some finite time or a finite number of iterations, they will stay in absolute value less than 1. So if we do some early stopping, we can always guarantee that we have sparsity of the method. If you go until full convergence, it's not clear, but then it's like forgetting about the prior in the end.
Okay, so is it correct to interpret it as well, the fact that there are some proximal iterations, and that these are sparsifying during the iterations,
yes,
means that the iterations will be sparse?
Yeah,
it doesn't tell you something about the, it doesn't necessarily show that the, when you get to convergence, the optimizer of the functional has this property, but at least the iterates have this property. Yes,
I mean, in general, the optimizer cannot have, because we basically minimize the loss. So if you would think you have a non-convex loss, or say you have a convex loss and you have a unique minimizer that is non-sparse, then we will converge to that minimizer. So we construct a sparse path towards possibly a non-sparse solution, but and then comes again this implicit regularization effect. So typically in stochastic gradient descent, you would stop to have a small norm. Here we would stop to have a higher sparsity.
Okay.
But
so there may be a difference with the classical inverse problem case, where it is also known that the very property of the functional that you're minimizing that involves the L1 norm implies that the optimizer has some level of sparsity.
No, that's not the difference. The point is, if you do inverse scale space also in the inverse problems setting, it's the same thing. The point is we are not minimizing a regularized functional, but we choose a path for the non-regularized functional. So it's only an implicit regularization or an iterative regularization, as we call it there. And so the properties are basically the same as for those minimizers, but what we show in the inverse problem setting, at least, is that these methods have less bias than the penalized regularization or the variational methods.
Okay. So
actually,
maybe
in some settings, this is something. So in some compressed sensing settings, at least, if you do the what they call refitting, so that you solve the L1 regularized problem, then you solve, and then you take the supports that you get plus the signs, and then you solve just the data term on this small support. This is exactly what you get from the inverse scale space method. So you can translate the regularization parameter to the time here, but you get this additional debiasing step for free, in a sense.
Okay, interesting. So is there a question from the local or remote audience?
Just a couple. I have one. Thanks, Martin, for the nice talk. With regards to the adaptive ISS, I was wondering, because you said also the to modify to the group sparse approach should be straightforward. But if I remember correctly, didn't we have some assumption that the regularization function had to be polyhedral or something? That in order for the, at least for the convex theory to work, then wouldn't necessarily be.
Okay, there are two levels of details. Okay, one thing, and this, if you want to have a piecewise linear or then this piecewise other behavior,
Yeah.
you need this.
Yeah.
If you're only interested about the first step, going from 0 to non-zero, then you don't need this. And here we only do this anyway, so we're not computing. I mean, we would still do all the linearized Bregman all the time with some time steps. We just want to get an estimate which parameters to exclude from the computation. So
Yeah, I see. Yeah. Okay. Yeah.
Otherwise, yeah. If you want really to do the adaptive inverse scale space, there is important.
Yeah. Also, you would have to solve lots of nonlinear problems for very small neural networks.
Yeah. No, you would never do that. Oh.
Yeah. No, thank you.
By the way, this group sparsity reminds me of a naive question. When you want to define groups to select neurons, there's two approaches that seem a priori equally good. You could group rows of the matrices or columns of the matrices, of the weight matrices. And you made one choice. Is it important or does it matter?
I'm not sure. I would say we don't have enough computational experiments yet to give you an answer. So,
well, somehow maybe this says that from your computational experiments, there was no clear superiority of one of the methods compared to the other.
No, I wouldn't even say that. I mean, I would say we started with the rows and we just did more experiments on that than on the others. So I would.
Okay.
The fact that so it's the fact that I show you rows and not columns is more because it was more our initial intuition and we did most experiments on that. It does not mean that results are better or anything else. So yeah.
Okay. Thanks. Are there more questions from the audience? So then I don't see any for the moment. Do you mind if I ask one more?
No.
So it's one about the theoretical analysis. It's as far as I understand, you make assumptions on the loss function. So some of the assumptions are related to the penalty, the regularizer, but some about the loss function. And I wonder to what extent they fit I mean, you were able to check that these assumptions fit the properties of the loss function in certain for certain neural networks.
Yeah. So I mean, one thing is the kind of sparsity assumption that the kind of smoothness assumption.
Yes.
That is fine as long as you do not really use the ReLU network, but as long as you smooth your activation a bit. There is some recent some results on gradient descents for really ReLU networks, which maybe one can adapt, but yeah, we are just not that far. So I would say in general, I mean, in the convergence of the objective, we don't need really other. So basically everything you can do for stochastic gradient descent, we can transfer basically under the same conditions. If what is a bit more interesting, if you think about convergence of iterates, really of the parameters themselves, then you need to make some strong assumptions. I mean, it's the same for, again, it's the same for stochastic gradient descent. The only point that changes here is whether you make these convexity assumptions or local convexity assumptions in the standard Euclidean geometry or in this geometry induced by the Bregman distance of the regularization. And that's, yeah, that's not always so straightforward to understand the convexity assumption or a strong convexity with respect to the Bregman distance. So that's yeah, that's an assumption that is basically impossible to verify from a theoretical point of view, I would say, at least with the current methods we have. But even the standard convexity is something that, yeah, let me check. Yeah. So for really training neural networks is something, even for one layer networks, is something you cannot really verify. Of course, if you do some linear toy problems, you can always do this. So, I mean, in a sense, I'm not concerned relative to all the results for standard stochastic gradient descent. I'm not concerned because we basically are at the same level of assumptions and results. Of course, you would always like to have more, but yeah, not sure how realistic it is to get more.
Okay, thank you. Are there more questions? Carola, do you see anybody raising a hand?
I think everyone seems happy. I mean, if you want, no, I should. Sorry, if you want, we can also move this to the coffee area now, and then maybe people can ask more questions if they want to. So I don't know how much time both of you have, but we have still planned in another 20 minutes or so for just chatting over coffee. So I would just take you with me with my computer.
This is fine. Yeah, it's my first time sharing a coffee break, moving, walking the coffee break remotely.
I mean, we could also just finish the official sharing and we can all relax and just chat and see if there are more questions if you want it. But so anyway, whoever has time to stay on, even online, is very welcome. Just go over to the other building now, and I hope I don't lose internet. But if I do, I will be back anyway.
Okay.
Thanks a lot, Martin. Thank you so much again.
Thank you very much. Very nice talk, Martin, again.